Just as a reminder, after 8 minutes, I'll give you a 2-minute warning. And then after 10 minutes, I'll stand up so you feel like a little bit uncomfortable. Wrap up, and then 2 minutes for questions. I think that's it. Okay, our first speaker today is Ray.
Okay. Thank you. All right, good morning, everyone. I'm Ray, and today I'll be talking to you about what Colin and I have been working on for the past 10 weeks under the supervision of Dr. Hogan, who's in the room today, and Dr. Meyer. So Colin and I, we worked on the same project, and because of that, we split our presentation into 2 sections. I'll be giving an introduction to the topic, and then Colin will be presenting the results that we got. So the field of research that we were doing our project in is cosmology. And for those of you who aren't familiar with that, it's the study of the origin and evolution of the universe. Now, at present, scientists believe that we have a good understanding of how the universe expanded from a hot, dense state, and the name given to this theory is the standard model of inflationary cosmology. So the important thing to know for now is that this theory is incredibly successful, and successful theories in science are those that are backed up by experimental evidence. So you may ask, how does a theory that described what happened like 13 billion years ago have like any credibility whatsoever, and like how do we feel so confident that it's correct? Well, you can imagine putting a probe up into space and then pointing it in a given direction. If you make it look at something that's, say, 13.7 billion light years away, you're essentially seeing the universe as it was 13.7 billion years ago. So, if you measure radiation from this direction, you can infer temperature from that point, and then you can do this for lots of different directions, and eventually you can create a map of the sky that assigns a temperature to each point in the sky. If you take that and project it down into a 2-dimensional plane, one possible representation looks like this. So this is a famous image known as that shows what's called the cosmic microwave background radiation. We can unpack this image a little bit. So colder regions are those that are blue, and then hotter regions are those that are more yellow. And we're just gonna talk about this picture for a little bit. You might notice that there's lots of like freckly patterns and stuff, and those are temperature fluctuations. And they look pretty random. And that's because they are random. In the standard model, it says that these temperature fluctuations come from vacuum field fluctuations, and since these processes are random, the model doesn't predict exactly what you would measure if you were to take a look at what the sky looked like, which may seem a little problematic since we want to use that theory to predict something. So, kind of to bring the point home a little bit further, on this slide I have a possible sky map that you may be able to observe given the standard model, and then on the right is what you actually see. Now, I can run 2 more simulations and show you that neither of these, or none of these, actually look exactly like what we see. One of the things that they have in common is if you zoom in on them, they kind of look the same, but this isn't a very rigorous test. So what is it that the standard model actually predicts that we should see? There's something called an angular power spectrum, which is a type of statistical measurement, and this is what it actually predicts with quite good precision. Essentially, it measures for regions of different sizes, the average fluctuation power in those regions. And this, because on this graph, the theoretical line, which is shown in black, matches up with what you actually measure, which is the blue data points on the screen. Since those match up really closely, we believe that the theory is correct. Now, there is a lot of physics behind this graph, and you can infer some stuff from it, but the only thing I really wanted you guys to get out of the last two minutes was that the standard model is a good model. And just to show you that these simulations have the same power spectrum, I went ahead and calculated it. It looks the same. Cool. Okay, so what Colin and I were doing was investigating a new hypothesis that kind of adds an additional layer on top of the standard model. And I just spent the last couple minutes saying that the standard model is great, so why exactly are we doing that? To explain that, I need to introduce a different statistical measurement that's called the two-point correlation function. So the best way to describe this is by explaining how you calculate it. You don't need to worry about what it means physically. But I said that we can create a map of the sky by assigning temperature to each direction that we point a probe in. You can kind of imagine this by having the surface of a sphere and putting a number at each point on the sphere. For now, we're just going to consider 2 points on the surface of that sphere that are have an angular separation of theta degrees. And then, of course, each of those points has an associated temperature. for now, what we're going to do is multiply those numbers and keep track of what that result is. We can go through and find every other possible pair of points with the exact same angular separation and multiply those numbers and keep track of them, which is what's being shown in the bottom left of the screen. And when you find all of them, you take the average value, and that gives you one data point in what's known as your two-point correlation function. So it's kind of a lot of work. You can do this for all the possible angular separations between 0 and 180 degrees, and then you can get a representative plot like this. This is just an illustration. So the standard model predicts super precisely what you'll see with the angular power spectrum, but it doesn't actually tell you exactly what you would see for this graph. So there's a lot of variation in what you might see for each simulation. So this plot kind of represents that. This is taken from a paper that was written like 10 years ago. And the shaded region represents sort of the outer bounds of what you might see, and the black line in the middle is the average of all of those simulations. Let's see how the experimental data shapes up to this. All right, so that's the experimental data. It fits within like the outer bounds, so that's pretty cool. In the paper, they actually say that this is totally consistent with the theory, which is correct. But there's two features that I want to point out, which I'll explain why they're of interest to us later on in the talk. But for now, it's going to suffice to say that one of the interesting features is that at around 90 degrees, it looks like it cuts through 0, okay? Or at least it's close to 0 around 90 degrees. Another interesting feature, which may seem a little bit more obvious why it's interesting, is the fact that it's negative at 180 degrees. So most of the simulations are positive around this area. And we just happen to live in the universe where it like literally is touching the edge. So if you're familiar with standard deviations, this is a 1 sigma deviation and this is 2 sigma. So this has like a very tiny chance of happening, but we're in that universe. And okay, to explain why they're so significant, I have to talk about spooky inflation. Spooky inflation is a new hypothesis that Dr. Hogan has developed, and it's interesting for two reasons. One is that it makes use of the holographic principle, and the holographic principle is something that's very closely connected to quantum gravity. Now, of course, quantum gravity is one of the open topics in physics that we really want to get answered. So if this hypothesis turns out to be correct, maybe it's a new way of probing quantum gravity. Who knows? There's some exciting physics that may be connected to this. Okay, so what exactly is spooky inflation? To explain this, I kind of have to go back to the cosmic microwave background radiation map. This is like a 3D representation of it, like assigning a temperature to each point on the surface of the sphere. The standard model says that the fluctuations in temperature arise from vacuum field fluctuations. And with spooky inflation, we still say that those fluctuations happen. However, we also are adding one more layer on top of that that says that points on the surface of the sphere can be entangled. So you can have 2 points that are causally separated, meaning that they can never communicate with each other, but through quantum entanglement, they have some correlations. Now, when you introduce new correlations like this, especially on a model that is inherently statistical, you get new statistics out of this. So there's new consequences. And it turns out that one of those consequences is that the value of the correlation function at 90 degrees should be exactly 0. And whereas the standard model has a lot of wiggle room in what the value could be, which is represented by this shaded region, this prediction has absolutely no wiggle room. It's like the value can only be 0. So the other prediction is that it should be negative around 180, but this prediction is not as strict. So we were mainly interested in the 90 degrees prediction. Basically, what Colin and I spent our entire 10 weeks doing was zooming in around that little circle and seeing if that value was consistent with 0. Meaning, is the measurement experimentally, like if you do all the error analysis, is 0 contained within the error bar region essentially? And there's a lot of fancy statistics that we still have to do about this, but that was the basis of our project, was pretty much seeing if it's consistent. So that just brings us to the key points in the presentation. I want to make some acknowledgements before I move on to Colin. So I'd like to thank the University of Chicago for letting me be here, the University of Arizona for supplying us with Colin's brain, and my home institution, the University of Texas at San Antonio. So if anyone has questions, yes.
Going
back to that previous slide, could you just go over what the numbers mean on the vertical axis? So what does it mean to have, like, for the correlation to be negative, and then, like, is it important that the numbers go from 0 to 1,000?
So correlations are, so when you have an angle of 0 degrees, you're measuring the exact same point. So you would expect that the same point is correlated with itself just because it is the same number. That's what's kind of represented by like having a really high value. So this is like a high correlation. Now when the number is negative, it means that when you multiply numbers, they end up being mostly negative. So that means that, let's say this point's positive and this point's negative, which is actually why I put them as red and blue. This would mean that they're antipodally symmetric or antisymmetric, meaning that like if the value is negative at 180 degrees, then points 180 degrees away from each other are going to be negative. So that's essentially what it's telling you. If the value is 0, it means that there's no correlation between the numbers.
And are those in the correlations of units of Kelvin?
So the units are microkelvin squared because you take a temperature difference and you multiply it with another temperature difference, so you just end up with Kelvin squared. Dan, you also had a question?
Oh yeah, what's holography?
Oh, well, I am so glad you asked this question because I just happen to have slides prepared for this. Okay, well, actually, wait, this explanation might go over 2 minutes. Okay. In this picture, we have like a painting of an apple, and it looks like the way that the light reflects off of the surface gives you some 3D intuition about this object in a 3-dimensional space. If I asked you to tell me if there was like a dot on the back of this apple, in real life, all you'd have to do is like look around the screen and then I would be able to answer the question. But because I can't do that, that information's just not represented in this image. So that may like bring you to ask the question, like, is it possible to take something 3-dimensional and then represent it in 1 dimension lower? It turns out that you can do that, and if you were to like look at very closely what that 2-dimensional plane looks like up close, once you've encoded the information on it, it looks something like this. Can anyone guess what this is an image of?
A toy van.
Yeah. I'll go with David's answer, even though Colin's correct. Yeah, this is an apple. So the point is that the information's scrambled. You can't really tell what it is just by looking at the surface. But there is a way of retrieving what the original object was, and you can do that by shining light through the surface. So now if I were to ask the same question again, I'd be able to walk around the apple and then see if it has a dot on the back of it or not. But the main point is that there's some kind of notion of this relationship between something in a 3-dimensional space and what's on its boundary, which is 1 dimension lower. So it's the kind of way that you explain how spooky inflation is holographic is in the sense that you're introducing new correlations between points on what's known as an inflationary horizon, essentially the picture that I showed you earlier. When you introduce new relationships between variables, you're reducing the number of degrees of freedom. So what I mean by that is, let's say you have 2 variables, you can specify them like separately. Okay, that's 2 degrees of freedom. But now if I say that there's a relationship between them, specifying one of them immediately tells you what the other one has to be. So you're reducing the dimensionality of the problem. In that sense, the spooky inflation is like a holographic model. Okay, but this is kind of cool visual